workshop. This is part number 1 of a series in which I'm going to attempt to make the smallest oscillating steam engine, or wobbler as some people know it or refer to it. So I'm going to go as small as I can. I'm hoping to make the entire engine about 9 to 14 millimeters long. So to put that into perspective, we're talking from here to here. So entire engine running this long. That's what I'm hoping for. Whether or not I get there, it may end up needing a bit bigger than that, but I'll try. So in front of me here, I've got a pair of engines that I made. Or when I say I made the base, I made the boiler. This one here, I made the complete engine. So this would have been maybe 1991 thereabouts. I made this as a teenager, probably one of my first machining jobs. So I machined everything, obviously the piston and cylinder and crankshaft. I also made the boiler, so yeah, teenager made a boiler, valves, control valves. I don't know where the centers have gone on those, but there's a safety relief here. Now this one here was actually given to me. It had I don't know where it came from, but I remember it had a boiler failure, and I was just given the engine, so I mounted on a piece of wood, put a line to it. I remember this one when it was running. It probably hasn't ran now in 20 years, but it revs really hard, whereas this one tends to be a slower revving and make far more torque. So I've measured the pair of these, and basically what you end up with is this one has a 1/4 inch bore, or 6.35 millimeters, and the stroke is exactly twice the bore. I've checked the one that I've made as a teenager, and I've just basically pulled some numbers out of my head and started building it. And this one was a 3/8 bore, and the stroke is about 15% more than the 3/8 bore. So that may account for the fact that it doesn't rev very hard, or maybe it's just a bigger engine, or I'm going to suggest that it's how heavy the cylinder was when I made it. But it does run nicely. So anyway, I'm going to try and stick with those numbers, but I've got a suspicion that I'm going to have to make the stroke a little bit longer to actually get it to work. So I'm trying to aim for like 1 millimeter piston diameter. So a 2 millimeter stroke, I think maybe a little bit hard. Might end up going for like maybe a 2.5 millimeter stroke and try and slow down how hard the little engine revs. Otherwise I think it may wear out before we get any actual video of it running. So anyway, yeah, stay with me and I'll take you through the tooling I'm going to use to build this. Now, because of how small this job is going to be, I decided rather than just use the jeweler's loop like I normally do held in my hand, I've gone all out and I've built this. It's obviously a Noga arm, or a simple dial indicator base. But what I've used, I've ordered this in, which was just a cheap off eBay sort of special. I think it was about $10 or $12. Had 2 LED lights and I think 4 sets of lenses, so you had from 10 times right up to 25 times. So I've chopped the lenses out. You can see these were out of there, and the little LED units I've removed from one and cable tied to this side. And then I've just ran the wire down the back. I cut the arm off of this side, which would be this bit here, and I've put some clear heat shrink over the switches there, so you can see that's a good little unit. And I can change the lens right out at the end. I can go from 10 times right up to 25 times, so it doesn't matter how small the part is, I should still be able to see it in the lathe, and the lights won't be in the way either. So this unit should come in handy, I'm thinking. Also maybe I can shoot the video through the back of it as well, so people can see what I'm doing. Starting with the crankshaft, I'm assuming that the crankshaft's probably going to be maybe a millimeter diameter, and I'm going to do it all out of one piece. It's not going to be multiple components soldered together. But the crankshaft itself I'm going to make out of a 6 millimeter socket headed cap screw. So I'm going to use this portion here. I'm going to chop the head off, chop the end off, and I'm going to do all my work, and the crankshaft is going to be within this. So yeah, it's going to be pretty small. Okay, I'm going to start by regrinding this tool. Now this is my smaller bench grinder. I've got another one over here and a linisher and whatnot as well. But the if your wheels don't run true on your grinder, you're wasting your time doing this sort of thing. Now I use a number of different dressers, but for a while now I've just been using a diamond dresser that's it's actually off a surface grinder that's had a handle welder to it, and I just run my finger along the front and then just dress like this on a slight downward angle, and you get a nice true wheel. I mean, obviously it's not for everyone, but I got a bit of a system that seems to work pretty well. But keeping the front of the wheel dressed, you can grind tools like this much quicker, and it cuts a lot cooler. But don't sort of have a grinder like this that you want to do these sorts of tools on, and then have people coming along sticking bits of Rio bar and whatever in there. You have a grinder just for doing your turning tools, especially if you're going to try and do this fiddly little work. So here you'll see I'm putting quite a bit of inclination on this so that the cutting loads are minimal. Basically I'm going for no radius. Now I'm going to use the side of the wheel, and I'm going to dress the top surface. That's perfect. All I would do now is get a hand stone and just break that edge so that it's maybe 1 or 2 thou radius at absolute most. Okay, I've got the tool set up in a vise just underneath here, and the jeweler's loop with the LEDs on it. Now you can see the tip of this tool, like there's my finger under there. I think it's a 15 times jeweler's loop I'm using. So you can see the tip of that tool, that really is sharp. So I'm going to break the edge just with this little stone I've got here. It's just a Toolmaker stone. I've got a number of different ones, different different grades, but this will be fine for what I'm doing. Now I'm going to break that edge so that it's not a completely sharp edge, but close to it. So when I'm doing this, I'm always cautious about, if I am making a burr, that I'm not making a burr that's going to make the tool blunter. So always pushing up towards that cutting edge. I'll just take the camera in and out of focus just to make sure it's got it. So you'll see it's broken that edge, but it'd be lucky to be a 1 or 2 thou radius at absolute most. So that's what I'm chasing. If I rub my finger down it now, the grinding marks are gone from the bench grinder there. It's just smooth now. So that's perfect. Yeah, because I'm making the entire crankshaft basically out of a socket-headed cap screw, the material you find in the shank here is it's great. It's perfect as far as hardness and toughness goes. So basically I'm going to cut the head off, or machine the head off, and I'm going to make the crankshaft out of this section here. So to do that, I'm going to hold it while it's in the lathe. Two options. I could hold it directly if I'm doing the turning of the section of the actual bearing diameter on the crank, not the big end where the con rod will run, but your crank diameter here. I could hold it with this. Now I've got these that fit into my spindle on my lathe. They're not a C5. People claim they are, but they're not. We did basically an online search around the world and had every manufacturer come back to us and tell us they can't identify who makes them. One's got a Rego Fix badge on them, the rest don't, so we're not exactly sure. We've checked them against Swiss lathes and whatnot, and they're a bit of an oddity. But anyway, to get around offsetting it, I can either use this to turning the diameter, which is the 1.5mm bearing diameter, or using a C5 collet block, I can put this in the 4-jaw and offset this in the 4-jaw, which will let me turn that crank diameter. Now if I leave this sticking out far enough and come in with, and all this will be tool steel, because razor sharp, a lot of inclination, so the tool will wear out quickly, but I'll have very low cutting loads. I can turn the little end, sorry, the big end where the conrod will run, and then I can then put this back running true without actually removing it from here, and I can get another tool in the back and finish turn it in one setup. But I'm going to counterbalance this crankshaft, kind of like this one here. So I reckon they rev a lot better when you've got this, when they're counterbalanced like this. So before I turn this back section, so I'll do the journal, the big end journal, and before I turn the back section, I'll probably throw this up in the mill and do the counterbalancing, and then I'll get in behind that with a tool. Now what I'm going to do is I'm going to use a tool on the back, basically this angle here. I'm going to penetrate down to the, maybe go down to 3mm diameter, just for a small portion, get a mic size on that, and then go off my digital readout, and I'm going to go down to the finish size, put heaps of rogue hole on it, and I'm going to creep back very, very slowly until I end up with the finished diameter. So basically I'll go one cut to size. If there is any polishing, it'll just be a very thin strip of wet and dry around it to polish from there. Yeah, you can't turn a job like this in multiple passes, and you can't use a live center either, because the offset is going to be 1¼ mm. So there's no way you can put a live center in the end either. Even if you wanted to turn a boss sticking out the end, I just don't think there's any way I could do it. So that's why I'm going to attempt to do it, see how we go. So I've got the collet block set up in the 4-jaw. You'll see that's a metric dial indicator there. So basically I'm going to start this crank maybe 1¼ mm. So I have to dial in the total readout will be 2½ mm. So you'll see there I've got that set up. Now I've got it mounted on the tool post there for a reason. After I've clocked, got close to my total run out, I'm just going to run it up these faces and just make sure that the collet block is in fact square to the chuck, and if I have to adjust it, then I'll clock again. Just do it 2 or 3 times till I get it close. No use just going on the diameter that you've dialed, because it might actually be on an angle, and you're going to end up with a journal or on the crank that doesn't actually run true. Seven, 1, 2. Okay, that's 2.15 mm there. There you go, 2.5 millimeters. Okay, it's within 0.1 over about 20 millimeters. So, seeing as the journal, the big end journal is going to be what, 2 millimeters long, 3 millimeters long. I think that's fine. You're talking microns. That's fine. Should be able to get a measurement off that and set the digital read out. Okay, I'll get a mic size off that. I'm guessing it's about 3 millimeters at the moment. .285. Okay, I'll mic it now and see what it's coming back at. It should be 0.8 or 0.805. Maybe a few microns up, sort of thing, something to polish off. Now when I mic this, I've got to be careful to only mic on the very, very front of the anvil. Any more than that and I'll bend the job. So I've got to brace my arms and whatever I can and just sit on the very edge. Okay, so the journal's finished. You can see that's 1.25 mil run out or 2.5 millimeter stroke. I ended up making the journal, it's about 5 microns under 0.8. So it's 795 diameter, so if I drill, I'm not going to be able to ream. I'm going to have to drill the bottom, the big end of the conrod. There's just no way I'm going to get a reamer that small. I could probably grind one up like a 3-point reamer out of a tool and cutter grinder, but I don't think it'll matter for what I'm doing. Okay, so I've moved the C5 collet block in the forejaw, and I've dialed the 6mm diameter, so it's running true. Now I've turned the outside of the crankshaft to 4.4mm diameter. Okay, I'll just give it a quick polish now. It's finished up at 4.4. It's about 5 microns up now, so just a quick polish on that surface, then I'll get it in the milling machine and put the cutouts for the counterweight into it. Okay, I've got the C5 collet block set up in my small machine vise there. I opted to use the small vise because it's better to get the jeweler's loop and lights and cameras and everything in there and see what you're doing. So I'm going to take the camera in a bit closer now so you can actually see. Okay, so I'm going to, same as you do at any other job, I'm going to touch on the top of the job here, but I'll witness it through the sight glass, and then I'll touch on both sides and use my digital readout to call that 0, and then I'll come down to the halfway point. So this is 4.4mm diameter. I'll come down 2.2 to the center line, and I'll go in until I touch that tiny little shoulder right there. Maybe stay a little bit away from it, but that's the bearing surface where the conrod will run against. So and I'll just machine that back. I don't know, maybe 3mm, and then after that's done, I'll turn it and I'll put the 60-degree brake on the other side for a counterbalance, and then it goes back in the lathe. Then I'll back turn this with a very, very sharp tool. So then the crank will be finished, one piece. That's one side done. Okay, I'm going to do the other side now. Okay, so the job's set up again. I'm going to take this cutter, and using the jeweler's loop, I'm going to bring this corner here down until it blends into that corner there, and that'll have a lead out of about 30 degrees. I'll do that to each side. Okay, I've turned the collet block over and set up to 15 degrees on the other side. Now I just need to get in and break this other corner, and then the counterweight will be 60 degrees. Then it can go back in the lathe. Okay, it's done. I can take it out. So I've got the job set up in the C5 collet block in the bench vise, and I'm basically trying to take the burrs off from the machining process. You can see here where my finger is, these edges here are all quite sharp, and trying to deburr it, I'm just trying to keep it in focus with the camera. It's quite difficult. At the moment it's the camera is actually about 1.5 meters away from a 20 times optical eyepiece, and there's a 250mm lens on the camera to try and keep this in focus. It's quite difficult to get the shot. So you can see that sharp edge there. I've been trying to remove these sharp edges and just give it a general polish. So I started off using small files, like needle files, and even in this image you'll see the needle files are still pretty big. They still look quite coarse. So I've gone back to using 1200 grit wet and dry wrapped around files, and then just basically bundling the wet and dry up so I can polish the edges off. Just trying to break those sharp edges, and I polished this radius on here. I filed this radius and then polished it, and then I've just polished all these edges around here, and basically taken the burr off without actually damaging this journal. So being very careful not to, no files or anything have touched this the journal here where the big end of the conrod will run. Okay, I'm back at the bench. Just going to do a quick rundown on how I'm going to actually make this back section of this crank. You can see here in this drawing, this is the crank here, which you guys have seen the other part. This head here is only 4.4mm, so less than 3/16 of an inch from top to bottom. Now all the front's all finished here. I've got to do this back section now, and what I'm going to do is I'm going to use this tool. I'm just going to keep the drawing here so the camera stays in focus. Okay, so you see this little tool here. This has been specifically ground up. Now you see it's got a back angle, like an inclination on the top edge. I'll just get my other hand on camera. See, this angle here comes down this way, and it's quite pointy. Now it's been stoned off at the front. I just stone it using just a small Toolmaker stone here, and I break going up on a slight angle, so you never ever roll that top edge over. It's just so there's a tiny little radius, so when you're feeding very, very slowly on the lathe, on a, basically on a tiny diameter, you have to take it right to the finished size in one cut, because the basically the pip is the job. The job can't support itself during the cutting, so you have to go down to maybe 3mm, 3.5mm diameter, and then go from there to the finished size in one cut. So lots of roll coal, very slow feed, and having a stoned radius on the end there gives you a nice finish. Now this tool here, I'm just going to get it in focus. So this tool here, I'm going to come in this back edge here, and I'm going to go into a set diameter, and I'm going to machine a small portion along, long enough that I can get a micrometer on. I'm going to use that diameter initially to get the digital readout set on my lathe, and then after that I'm going to go all the way down the back, and then I'm going to go along. And one thing, before I go too far, I'll probably go 2 millimeters along, and then I'll pull out. At that point I'm going to do a trial on that diameter. I'll show you how I'm going to measure that, because it's too small to get in there and you know, with a standard micrometer. And if I go a full you know, a full length all the way along so that I can get a micrometer in there, then the first section won't actually support its own the cutting forces if I was to actually try and go deeper. So what I'm going to do is, I've got a 60 thou slip gauge here. Now 60 thou, as I've put on the drawing right there, you'll see 60 thou, it's 1.524 millimeters. Now the reason I'm bringing this up is the only tool that I have that'll fit down there is my digital vernier. Now this is a Mitutoyo digital vernier, so they're pretty good. But if I measure this, you'll see there it measures 1.51. So measuring on an actual a known slip gauge, and I've checked the slip gauge against my mic, it's bang on. So basically I'm going to use this digital vernier to reach down into that small area. So I take a cut first, and then I'm going to get down in that little area where it's only maybe 1.5–2 millimeters long, and I'm going to use that. Now, knowing that my vernier is reading about 0.1–0.14 small, I know the size I actually have to hit just using digital vernier. So just as a precaution before I finish. Now I'll probably leave that diameter on the crankshaft about 5 or 6 microns up in size, and then I'll give it a polish at the end, because it is in fact a bearing surface, and there's no way I'm going to be able to spin this thing up to the proper cutting speed for the tool, so I'll just have to polish it to get a decent finish. But I'll do some close-ups of the tool. Okay, so I've got the C5 collet block back up in the forge yaw. You can see I've got the emery cloth in here again. Makes it nice and easy to move it around basically without putting big marks into your collet block. Now this dial indicator you'll see here, it's a micron dial, so it's 10 times more accurate than a standard dial. Now I'm going to clock that previously machined diameter, and then I'm going to come in with that sharp tool and get down that back face and machine the 1.5 millimeter diameter. So I'll zoom in with the camera so you can see. Okay, first I'm going to use an eyepiece to set the tool, 3 or 4 hundredths back from that front face. Then I'm going to machine that counterbalance with probably 7 or 8 hundredths, thicker than it needs to be. And then I'm going to get in there with a digital vernier and just measure that thickness. I would like to use a disc micrometer, but the disc mic won't actually fit between the collet and the end of the crank, so I'll just have to settle for a digital vernier.
Okay, that's just a little under 01 up on size, so I'll give that a quick polish and then I'll use the same tool to part it off. I'll start parting it off and then I'll break the corner with wet and dry before I part right through.
Okay, all done.
Okay, I'm back at the bench. I've parted the crankshaft off. I give the end a bit of a polish. It's a tiny little component. I put it on the scales and it weighs in at a whopping 0.24 of a gram. So it's turned out quite well. I'll just put it on the drawing so you guys can have a look. This way the camera will stay in focus. So it turned out quite well. I'm thinking episode 2 I might do the main body out of aluminium bronze. So if you found this useful, tune in for that. Thanks for watching.